that means the maximum amount that you can, so I should say max, right? The maximum amount that you can give to an electron is all the energy of the photon. And then minus the work function of the metal, minus how hard it is to get it off the metal. You're going to take some work to get it off the metal, that's why it's subtract this part. A few things here. This is only the maximum energy because this is not a fully efficient system or anything. The photon, when it hit the electron, will often bounce it the other way, right, where it just kind of bounces around in the metal, thus, wasting more of its energy, right? More of its energy is absorbed in other places. And so this is not exactly the energy of every electron. It's just the maximum case scenario. Usually there's other stuff that absorbs the energy. Okay. Now, a few things. Why does this require a particulate view of light? In other words, why does this not work for a wave view of light? Good. Waves are an extended scope, right? A wave of light kind of can wash over many particles at once, right? A wave exists over a space, right? So you'll have several electrons being hit by the same wave. So then, if you increase the amplitude of the wave, you will increase the amplitude of what you're giving to all those electrons, and it'll be all of them, right? What you should see with wave behavior is a kind of pumping effect, where the current from the photoelectric effect would get larger over time, because as you pump more energy into it, the electrons will get more and more excited, and then you can start knocking them out as you fed in more energy. But you don't see that, as you may have noticed, right? You just see the thing snap right to one spot and stay there. So the key to understanding it is the particulate behavior. In addition, there is also an effect that's going to happen when your frequency of light gets too small. Tell me what happens when the frequency of light gets too small. Can your max energy be negative? No, it's kinetic energy. Kinetic energy is not allowed to be negative, right? I know. So instead, what's going to happen? What's going to happen differently? Right. So if this is too small, right? If HF is less than 5, right? Then remember, this is the energy of one photon. One photon will not give enough energy to one electron, and therefore it'll hit the electron. The electron will kind of bounce, but not get out of the metal, and then it'll settle down again. That'll be dispersed as heat, and then another photon hits it, and it'll bounce again, and so that. And what will happen? No current, no photoelectrons, right? So what this also predicts is that when your frequency gets too low, you get no photoelectric effect. This, again, is something that would not be predicted by a wave model of light. A wave model of light would be like, well, if you have low energy, you can still, again, you kind of pump it up, right? If you put it over wave energy over a while, you'll get enough energy to knock these things out, right? Instead, you have what's called the cutoff frequency. Below the cutoff frequency there is absolutely nothing. Unfortunately, we do not have any filters that are below the cutoff frequency, which I find annoying, because I would love to show you guys the cutoff frequency. But you notice that you were getting close, because those red ones don't work well. You notice that? The red filter, you get to really get bright light to get a decent current out of it, right? That's because you're approaching the cutoff frequency. And when you're approaching the cutoff frequency, you have a lot of trouble getting anything off of the metal. And so if we had something a little bit farther into the red, it might have to be infrared, I'm not sure. Then, but if we got light in a bit lower frequency, then you would actually get nothing at all on outright the light.
It's the same.
Yeah.
Right
It's a kind of the filters, and I have not been able to find any online. Because I think what it is they don't want to give you equipment that they know doesn't work. You know what I mean? Like you put this in and now nothing happens. Okay, great use of your $1,000 total electrical effect cost, right? So I think that's why they don't sell those. But it would be nice to demonstrate, I think. But I've not been able to find them. Otherwise, I'd love love to do that to you with my brain, right? Okay, try this one, guys. Put it black, right? Yeah, put it black. Yes.
So why does the effect always be present?
In a wave model, the energy is not localized. It is not affected to a single particle, right? The energy is distributed across the electrons in the metal. Because of that, different electrons will get different amounts. So say you're right below the cutoff frequency, right? Because there's a distribution among different electrons, some of the electrons will still come out, right? It's also in a wave model, you can shine very bright light at below the cutoff frequency. So the cutoff frequency for us is like infrared, right? So you can shine very bright infrared light. It would have a lot of energy, so that energy would hit the electrons, distribute among them, and knock them off. But in the particle model, it would be very bright light, but each photon is very low energy. So each photon hits an electron, doesn't work. And another photon hits the electron, doesn't work. And so nothing comes out. Okay? Let's say in the wave model, you just make it brighter, and then you get more energy, and then it pulls more things off. But in a particle model, it's about the energy of each particle, not the total energy of the whole beam. And that's what makes everything work. Okay? The photoelectric effect is very important and not simple to understand. Frankly, I taught this class several times before I really felt like I understood it. But it's worth thinking about. It's not an obvious one. It's not a straightforward one. It's quite subtle. That's why they gave him the Nobel Prize for this, right? He didn't do a single experiment. He just explained this part, and everyone's like, oh, that. Okay, and the more you think about it, the more you're like, wow, that explains everything. It explains every experimental part. Let me give you a brief historical aside about that does not require anything that you really need to know, but I think it's worth knowing about where this number comes from. Okay? It comes from what is usually tracked as the very beginning of the study of quantum mechanics. That is a German physicist named Max Planck. But we say Planck because we're Americans. And Planck is spelled P-L-A-N-C-K. Germans can't spell, right? You know. He was working on black body radiation, which we don't need to go into in detail. Black body radiation is the energy that is given off by hot bodies. I love this, right? So anything that is hot gives off radiation. They say black body because it's more complicated if it also reflects and things like that. But black body, what does black mean in terms of light?
It absorbs all light.
It absorbs all frequencies. That turns out to be by far the easiest to calculate. So you use black body as an easy approximation. If you're not black, there's reflection of light, then it gets much more complicated, so no one wants to deal with it. So they talk about black body radiation, the simplest idea of an ideal body that doesn't reflect any light, that emits heat, emits light, naturally. So we do that, for example, because we're hot. We are hotter than our environment, so we emit light. Have you noticed? Well, you can if you hold your hand right here. Hold your hand right here. What do you feel? No, don't touch. Without touching. What do you feel?
This is pretty.
Right? If you want it extra fun, do it to someone else. Right? If someone else closes their eyes and you hold your hand, not touching their cheeks, can they tell? Yeah, you can tell, right? Why can you tell? What do you feel?
Sadness.
You feel heat. Where's the heat coming from? Your skin's a very good insulator. It's not leaking out of your skin. That's the heat in between. The parts in between your hand are not hot. Okay? So where's that heat coming from? Your body is radiating heat. Your body is radiating infrared in particular. It radiates because that's the black body spectrum. It radiates infrared, and that heats that your skin feels good, heats up slightly as a result of the infrared. Okay? Your body's radiating all the time, so you see this like Predator or something. They have those like old passive infrared scopes where it says like the red blob surrounded by the blue everything else, right? Cool things like the wall do not radiate much infrared, they radiate a little bit, right? Hot things like us, because we're warm-blooded, so we're much hotter than the environment, we radiate lots of infrared. And if you get something really hot, like a piece of metal, and you get it really, really hot, what happens? Ooh. It glows because you get it up into the visible spectrum, right? It gets bright enough to go into the visible light, and then it starts glowing. It starts at the low frequency light, which is what color? Red. If you get it really, really hot, it'll start turning yellow, and then eventually it'll cover the whole visible spectrum, which means it'll be white. And as you get it really hot, it actually gets the bluish tinge to it. And then by then it starts releasing ultraviolet radiation and stuff like that. from which we can actually figure out the temperature of stars by looking at their color. All right, so this all stuff. What he was trying to do is calculate this from first principles. Where does this actually come from? It comes from an atomic view. You look at atoms and imagine them radiating. And here's the problem. If you do this right, this is what it looks like. Okay, this is a distribution of, so this on this axis is frequency, and this is intensity. So this is like a distribution of how much you emit of each frequency. So for us, this right here is in the infrared. Okay, and we emit very little in the visible region. Technically, we emit a little bit, I think. I don't think it's enough to see. So here's the thing. Planck did the calculation. He did everything right. But when you do the calculation, it goes like this. So this is theory. This is experiment. Okay? Not so good. Right? What does the theory predict? It diverges. It goes it's an x to the fourth behavior, actually. And so it predicts that as you go higher frequency, you emit more and more and more of higher frequencies, which means, according to them, we emit some infrared, a lot of visible light, even more X-rays, and a ridiculous amount of gamma rays, which is clearly not true given the fact that we are alive. Yes, Mike?
Is this the reason why the cutoff frequency solves this? Because
no. This is well before this. Sorry.
Okay.
Really completely separate from this. Sorry. Now we're talking about a different problem of black body radiation. Thank you for clarifying that. Yeah. This is completely separate from photoelectric effect. This was known, and because it was the 19th century and everyone took themselves a little bit seriously, this is referred to as the ultraviolet catastrophe.
Me too.
Seems a little bit much. The ultraviolet catastrophe, it refers to the fact that in the ultraviolet end, meaning the high frequency end, that theory and experiment did not line up. It was not an event, no one died. Yeah, I know, right? It sounds like something much worse than it is.
I thought they were referring to that if this was real, everyone would be dead.
Yeah,
I mean, we would be.
So that's the ultraviolet catastrophe, that's the name of it. Planck solved the problem by making a completely random assumption that he didn't play snowball by luck. He stumbled on it by math. I mean, he figured out, wait a minute, I can make this work. He basically realized, he looked at this thing, and what he had is you have a bunch of atoms vibrating, and you do these calculations to figure out what frequency they come out with. And to do that, you take an integral, the sum over all possible energies. You do an integral over it, you get this. And he said, wait a minute, I know math, and I know that the integral looks like this, but I think you get something more like this if you take a discrete sum. In other words, instead of an integral, you use a regular summation, a discrete sum. So he makes, with no physical motivation, he says, what if all photons, they didn't have the fact that much, but again, all light is emitted in multiples, let's try this again, energy with multiples of h as frequency. In other words, instead of saying you can emit light however you want, he said, I'm going to require light to be emitted only in integer multiples that are proportional to frequency, some constant times frequency. Why? In fact, I've read Planck's original paper in translation, and he totally buries this in the middle of the paragraph. He is trying to hide it, I'm pretty sure. And he is not being like, look at this great discovery, guys. I think he is trying to hide this part because it doesn't make any sense. Why would you take a discrete sum over energy, right? Why would you say, oh yeah, you can have this energy and this energy, but nothing in between? Right? There's no justification given. He really tries to keep, he just says like, and then we take a discrete sum over that. And then we got this, right? And so everyone's like, but here's the thing. If you do that, then it works. Okay? And given the experiment that already existed, you can, so you already know the right number, you can adjust that number and solve for h, right? H is just a constant, so you can find the number, solve for h, and that number, as I mentioned, is 6.68 times 10 to the negative 34 joules a second. That's called Planck's constant, because Planck was the one who discovered it, even though he had no idea what it meant.
Do we know any idea why? Do we now know?
Do we now know? Yes. Now consider Einstein. Now, when Planck discovered this, they didn't have Nobel Prizes yet. So he did get things named after him, like the Max Planck Medal and the Max Planck Institutes in Germany. Because he was a great scientist, don't get me wrong. But he did not have the inside of Einstein. Because face it, no one else did. And so Einstein looked at this and came up with this explanation. Okay, connecting it because he used the same constant. Okay, Einstein not only explains the photoelectric effect, he also explains the blackbody effect. Here, what it says is light is emitted in energy with multiples, integer multiples of HF. Right? Now, Einstein gives an explanation. When you emit light, you can't just emit any amount of light. You have to emit a particle of light, right? And that particle comes with an energy of HF. So why is it integer multiples of HF? Yeah, because it's that many particles. So if you have 9 HF, 9 times HF, that means you send out 9 particles, right? So Einstein interprets this as this integer multiple here that Planck used is actually just the number of particles of light. And it makes perfect sense now. Yeah, you can't shoot out half a particle of light. You can only shoot out 1, 2, 3, right? Not 2.5, not 5, right? So Planck's kind of mathematical deduction that worked with theory, Einstein gives a physical reason. Pretty cool. Won a Nobel Prize, and it was one of the least significant things he accomplished that year. Isn't that crazy? It's crazy. Yeah. So the blackbody, the whole thing, this was the assumption that if you do it, it makes sense. Okay, I'm not going to work with the math. The math is far too complicated. So that's why I used to spend more time on this. This is really just historical. Okay? The key is, this key assumption is what makes all the math work. You switch it from an integral to a discrete sum. You don't allow every energy, you only allow integer multiples of h times the frequency. And Planck did it just because the math worked, right? But Einstein says that makes sense. The integer multiples of h times frequency, that's just saying the number of particles, of light particles you're shooting at.
So is there I guess this is a little bit more deeper, but is there a reason why the light has to?
What an interesting question. Yes, there is a reason. Can I explain it to you in this class? Probably not, but we'll work on it. Okay, we will learn a lot of things about this. So this blackbody radiation, which was in 1890, is considered the beginning of the first quantum experiment. Remember, in 1890, this is when people thought that physics was basically solved, right? We had a few unsolved problems like reference frames and Maxwell's equations, right? And then here was another unsolved problem, but ultraviolet catastrophe, the blackbody radiation not working, right? Oh, look, Max Planck solved it. Great, we got it solved. I mean, it doesn't quite make sense, but we'll probably work it out. Well, we did. Einstein says, here's the solution. Everyone's like, thanks, Einstein. And after that, after the hoopla, the Nobel Prize, okay, the Nobel Prize was 13 years later, but anyway, after that, everyone's like, hey, great job, Einstein, then they're like, wait a minute. Okay, now, tell me what the wait a minute is. This is what probably a lot of you have been thinking, hopefully. What is the big wait a minute here? Go ahead, Bendy.
Is light a wave in a particle?
Right, because didn't I just tell you that in 1805, Thomas Young performed an experiment that we call double slit, right? The double slit experiment. And what happens when you shine light through a double slit? You get a, what's that called? What's that? Well, what's the word we use for it? It starts with an I. Is it the top of the part? Oh, we gotta go over that one.
Interference.
Interference. There's an interference pattern. Speaking of which, we can probably go over that in a second, because I'm in the middle of something. Interference pattern, right? That's what we call it, where you go light, dark, light, dark, light, dark, light, dark. Interference pattern. Okay? So you said, wait a minute. We knew since 1805 that light has an interference pattern. What behaves like an what thing gives you an interference pattern?
Waves.
Waves give you an interference pattern. Only waves. Particles do not give interference patterns, right? Because waves work because you have positive and negatives in the wave, and the positives and negatives can cancel out. But if you're throwing rocks, you do not have positive and negative rocks, and two rocks when they hit will never cancel out, right? So we had established for 100 years, exactly 100 years in fact, that light was a wave. Furthermore, what other thing shows the light is a wave? This was for a while ago, but we did it in this class. Remember something we did with light towards the beginning of this class? It was been a while. Big discovery. James Clerk Maxwell, with Maxwell's equations, showed that light was an electromagnetic wave. Remember? The travel at the speed of light. Remember that? That was where all the problems started, right? So he showed again that light has to be a wave. right? Like even more solidly, more conclusive. So both experimentally and theoretically, light has to be awake. And now Einstein says the only way to understand these things is that light be a particle. And he's right, it explains things perfectly. But, hang on, right? What's going on with our light?
Is light both a particle?
Light's
So
changing
is
on
light a
us.
particle? Is it both? Is it neither? Is it a switch?
Yeah.
Right? So,
Change.
clearly, there is a way to deal with this, right? We are scientists, we can experiment to do this. But we're not actually doing the experiment, it's not that easy. But we can talk about the experiment and I can tell you what happens. So, how can we make it so that we can figure out whether light is a wave or a particle, or when it's what, or whatever, right? What do you think?
Combine the experiment.
Okay, combine the experiments, how do you do that?
So you get the double slit experiment, you get the interference pattern, put it onto a sheet of wall.
Yeah, well, that's so then you just got a bunch of electrons shooting out, right?
Or
Yeah, no, here, let me do it this way. This will help a little bit. If light is made up of photons, let's say you pass light through a filter that cuts out 90% of the light. Okay? We make this filter. You've seen them. They're sort of spoke glass, right? A dark glass, right? So that it cuts out some percentage of the light, 90% or 99% of the light. Okay? Now, what happens if we pass it through another one of those, and then another one, and then another one, and another one? Eventually, what's going to happen, according to what Einstein's theory is? What's going to happen eventually? Eventually, we're going to have what? Eventually, we're going to cut it down to one photon left. Like if you got a billion photons, passing through those filters, it's just sort of probability which ones get through, right? And you cut it down to 10 million, and you're like, no big deal, right? It might not be exactly 10 million, but like, by probability, it'll be about 10 million, right? But eventually, if you have two photons, right, and you pass through one of those filters, it really becomes just a matter of luck which photon gets through, and eventually you can cut it down. So there's one photon getting through occasionally, right? In other words, it's possible to put enough filters in front of a light source so that you can cut it down to a single photon. So that would be the first test of does this actually happen, right? Cut it down to a single photon, shoot it at a piece of photographic paper that will expose when light hits it, right? And light never goes in a perfect stream, especially back then they didn't have lasers. So because of that, the things will hit at different spots, right? And so you'll get blip, blip, blip. And you'll be able to see if it's a photon or not, right? Because you should see individual particles if you do that, right? Well, guess what? You do. Sure enough, you see individual photons. So Einstein's theory is confirmed. If you cut things down, cut the light down enough, you get individual photons hitting pieces of paper. That's exactly what the photoelectric effect explanation said. So it's not a big revelation, but it's still weird, right? So now we know we can shoot things off one photon at a time. Okay? So now that we know we can shoot photons one photon at a time, now give me the experiment we should do. Now that if we can shoot photons one photon at a time, shoot photons one at a time through a double slit, right? So we're going to do the double slit experiment.
Boy.
One photon at a time.
Wait.
You see, because normally you shoot trillions of photons, right? More than that, really. And you shoot them all through there, and they all, you can say, well, a whole bunch of them together acts as a wave, right? So you get a wave going through, and the waves interfere, and blah, 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 right? When you have a very small number, you can shoot individual particles. So the big question is, what happens if just one photon goes through? Right? The argument would be that the particles maybe somehow, in aggregate, when you have a lot of them, somehow all the particles act as a wave. Now, it's not immediately clear how that would happen, but at the same time, you can kind of imagine it, right? Or just, hey, where'd that one go?
Me too.
What a pain. I have to look it up. Sorry. I have a video to show you.
Video.
I know, right? Exciting. Well, you know what? How about while I look for the video, I give you the answer.
Photon go through polarized.
That's also exciting.
Me too.
not as
The thing was though, is it developed a lot whether the photon is doing that?
Okay, ready?
What about quantum electrodynamics and
By
the
the
thing
way,
with the triangles?
I uploaded the.
Okay, so number one,
He uploaded the sheet.
Okay, no one's gonna be able
By
to
the way,
submit
you
it
guys
since
know
he's
by
doing
now
it.
that I don't have,
No one's submitting it.
it's a pain for me to post the answer keys. So it's up to you guys to actually write down answers if you don't have them, right? So just be aware of that. Okay, number one is 50 microns, or if you prefer, 5 times 10 to the negative fifth meters. Number two is 643 terahertz, or 6.43 times 10 to the 14th hertz.
Why does she talk so fast?
6.43 times 10 to the 14th.
6.43 times
The
10.
first one is 5 times 10 to the negative fifth meters.
So two different answers for number two. Two different.
No. Number one is 5 times 10 to the negative. Oh,
I'm talking about.
I see you're talking about. No, it's the same thing in different units.
Okay.
It's probably easiest in hertz. So 6.43 times 10 to the 14th hertz. Number three is 10.8 meters.
Number 4.
Your mom.
Number four is 3.125 meters.
This is for 18.
Number five is C and D. Number six is B. Number seven is C. Number eight is D. Number 9 is A. Number 10 is B.
Is this for homework 18?
I think it was the homework before the lab. Yes. That's a lot of.
Any questions?
How are you today?
What?
Nothing.
No? Yes. What's remarkable about YouTube, which is such a great, a great way of cataloging all sorts of cool stuff, right? Like the intros and episodes of stupid cartoons from the 80s. You know, there's one called Rubik the Amazing Cube, a cartoon based off of Rubik's Cube. It's amazingly bad. So it's probably about as good as you think it is.
This is gonna be amazing.
But with all of that, when I look up, that means YouTube has the ability to show you the actual double slit experiment I'm talking about here. And yet, when you look for it, all you get are cartoon drawings and people talking about the double slit experiment. Where anyone can talk about it, the uniqueness of YouTube is that you can actually show you the double slit experiment.
I feel like this
And
could
so,
be a meme.
that's annoying.
What, in ranting?
So, I'm going to show you the actual double slit experiment, provided this works. Because this is not on my computer. Oh, it's one of those kinds. I see.
Why does the projector have its own IP address?
Oh, it does.
Alright, let me explain to you. Actually, got the other one. It's a little hard to see. It's just a 20-second video. Alright, this is. Okay, it's not quite my favorite video on YouTube because the dramatic master is also good. But the, I don't know, Rebecca Last Friday, there's a lot of them. But this is really this is my favorite, like, real video on YouTube. There are a lot of cool phenomena in the world. This is